In this video, we'll start to learn about alkenes and nomenclature. When we look at alkenes, those are our hydrocarbons that contain a carbon-carbon double bond. We sometimes call them olefins. And so this means that in our alkenes, it contains at least one carbon-carbon double bond, but it can contain more. So alkenes are our functional group where the carbon is sp2 hybridized. And some examples of alkenes that occur in nature is allicine, which is responsible for the odor of garlic, geraniol, which is responsible for the smell of roses and is sometimes used in perfumes, and alpha-farnesene, which is found in the natural waxy coating that you see on apple skins. And you can see all of them contain a carbon-carbon double bond somewhere present in the molecule. The allicine and geraniol contain other functional groups as well. But in this chapter, we're going to focus on the carbon-carbon double bond. When we compare alkenes and alkanes have fewer hydrogens than the alkanes with the same number of carbons. This is sometimes referred to as unsaturated. So here we have an example, ethylene, which is C2H4 versus ethane, C2H6. So you can see both of them contain two carbons, but the ethylene, the one with the double bond or alkene, only contains 4 hydrogens versus ethane, which contains 6. So because the ethylene has less hydrogens than the maximum possible ethane, we consider it unsaturated because there are fewer hydrogens. A quick reminder on how to calculate hydrogen deficiencies. We saw this earlier in the semester, and now we're going to review it again real quick. So if remember, our hydrogen deficiency, or HDI, or sometimes it's called our unsaturation, that's going to equal 2 times the number of carbons plus 2. Remember that formula there? This gives us a fully saturated compound. Then you subtract out the number of hydrogens, subtract out the number of halogens, and remember, add the number of nitrogens. Take all of that and divide it by 2. If you use this formula here, you can figure out the degree of unsaturation or the hydrogen deficiency for any molecule. And so if we have an alkene, that is a functional group that contains a pi bond. And remember, each pi bond that's going to equal 1 degree of unsaturation, or 1 HDI. So if our molecule contains 2 alkenes, that would have an HDI of 2. And remember, the other way you get an HDI is if your molecule contains a ring. So each ring is also going to equal 1 deficiency, 1 HDI. So I'm sure you're asking yourself, why do you care about alkenes? Alkenes are really important compounds. Alkenes are really important compounds in the chemical industry. So in the chemical industry, about 70 billion pounds of propylene or propene and 200 billion pounds of ethene or ethylene are produced from petroleum every year. Petroleum is the oil we get from the ground. And so 200 billion pounds of that a year is used to make ethylene. And then another 70 billion pounds every year is used to make propylene. These are 2 precursor compounds that can be transformed into all sorts of functional groups and all sorts of different compounds that can get later on used in various parts of our daily lives. So if we take our petroleum and our ethylene and propene, ethylene can get turned into ethanol, or the alcohol that we drink or use for cleaning, can get turned into ethylene dichloride, ethylene oxide, vinyl chloride, which can be used for plastics like PVC, can get turned into acetaldehyde, which gets turned into acetic acid or vinegar. The ethylene oxide gets turned into ethylene glycol, which is also antifreeze. And then the propylene, that can get turned into polypropylene or plastic. Isopropyl alcohol or rubbing alcohol. Rubbing alcohol can get turned into acetone, which is also nail polish remover. Propylene oxide can get turned into propylene glycol, which is commonly used as a food additive. It is also used as antifreeze. So all these different compounds come from two precursors, ethylene and propylene. So our alkenes are a very important functional group and a very important part of our daily lives. And soon you'll learn how to do reactions that'll convert our alkenes into different functional groups here. But before we do that, we always got to learn how to name our compounds. So we're going to look at nomenclature with alkenes. We've seen nomenclature with alkanes, now we're going to look at the alkenes. So first thing is you want to identify the parent chain, just like with the alkanes. They follow a similar set of rules. So first we identify the parent chain. The parent chain in this case has to contain the double bond. So we're going to name the parent chain, and instead of ending it at ANE for an alkane, now you end in ENE for an alkene. So you can see the naming here, the ending of the parent chain, kind of goes and tells you what the functional group is right away. So for example, with our parent chain, let's say we had this sort of parent chain. We can see there's 1, 2, 3, 4, 5 carbons. So of course we call it pentane. Now, if I put a double bond in there, it still has 1, 2, 3, 4, 5 carbons. So it'd become a pentene. ENE versus ANE. And so as I said before, the parent chain should contain the double bond. So for example, we had these two chains. We can see with the alkane, our parent chain has 1, 2, 3, 4, 5, 6, 7, 8. So the parent chain has 8 carbons. But now with our alkene, the parent chain should contain the double bond. So instead of going directly across the bottom here, I have to include this double bond. So here we start 1, 2, 3, 4, 5, 6, 7. Now the parent chain only has 7 carbons. So that means the parent chain for our alkane would be octane. And the parent chain for the alkene, that's going to be heptene. This way we can be sure that the double bond is included in that parent chain. Once we've determined the parent chain, now we're going to go and identify and name the substituents. For this, we use the same rules that we did for the alkanes. So if you remember your rules for alkanes, now you can use them for the alkenes as well. And then we also want to assign a location. We typically want the location to have the lowest number possible, right? We typically want the substituent to have the lowest number possible, with one exception. In this case, the double bond is more important to have the lowest number. So the double bond has a higher priority versus everything else. So we want to make sure we give the double bond the lowest number possible. Which means if we look at our compound here, and you want to try and figure out its numbering, we have two options. You can either go from left to right or from right to left. So you can either number 1, 2, 3, 4, 5, 6, 7. Or we can go 1, 2, 3, 4, 5, 6, 7. So now when we're thinking about these possibilities, if you didn't remember that double bonds are high priority, you may think about using the top or the blue ones, because that gives you number 2, number 3, and number 5. If we use the bottom ones, we also get number 2, number 5, and number 6. So not quite the same. But if we use the bottom ones here, the double bond gets the lower number. It gets the number 2, because that's the one it starts with. If we use the top numbers, it would get the number 5. So when we're trying to name this one, we would use the double bond to dictate the direction we start with. So here we start with the black one. And that means this would be 5, 6 dimethyl hept 2 ene. This way we can tell the location of the two methyl groups and the location of the double bond. So remember, we want to list our substituents in alphabetical order, just like we did with the alkanes. So we're using those same rules still. And then when we do our double bond and put its location, we place the number just before the suffix. So again, when we had our drawing, we can see that this would be 1, 2, 3, 4, 5, 6, 7. So it'd be 5, 5, 6 trimethyl hept dash 2, because that's where the double bond starts, ene. And then if we had more than one double bond, I would include the numbers right here and then say diene or triene or tetraene. So let's practice this. Let's say we had these three compounds and wanted to figure out what their names were. Use the rules that you just learned, try to figure out the names, pause the video, write down your answers, and then unpause the video to see if you got it correct. Okay, so with our first one, we can see the double bond starts at position 1. So we have 1, 2, 3, 4. So if I wanted to write this, it would be butene. If the double bond starts at the first position, we don't need to include the number. If you wanted to include the number, you can have but1 ene. But since it's also the only functional group, butene, easy enough to do. Our second one, Here we have a ring. And we have a substituent off the ring and 2 double bonds. So we got to figure out where to start our numbering on the ring. We want a number so that the substituent gets the lowest number possible. So when we number the ring, we want to start here. 1, 2, 3, 4, 5, 6. If we do it that way, we start with our double bond, so it's the lowest number I can have for the double bond, and the substituent gets the lowest number. If we started with the other double bond, we'd have 1, 2, 3, 4, 5, 6. That would end up giving our substituent the number 3, a higher number than 2. So that means the name for number 2 here is going to be 2 ethyl, because that's an ethyl group, cyclo, hex, and since we have 2 double bonds, 1, 3, diene. And then finally, looking at number 3, we can see we have a substituent, and the substituent contains a double bond, so we're going to have to name it. That substituent can either be named as methane, or more commonly, we use the common name, just like ethylene, it becomes methylene. And we tend to use the extra YL-ene here for 1, 2, or 3 carbons. So methylene, ethylene, and propylene. So that means the name for this compound would be 3 methylene cyclohexene. And remember, we don't have to include the number for the double bond in the ring because that starts at position 1, and that's the only double bond we have on that ring. Let's go on into a little more detail about naming these alkenes. So if you remember when we talked about stereoisomers, we talked about cis-trans isomers. And technically speaking, the cis-trans modifier are strictly used to describe a double bond with identical groups on each carbon. So if we look at trans 2-pentene, so here we have our double bond starting at carbon 2. So carbon 1 is up here. And then we have our ethyl group on the other side. What are the identical groups here? Not the methyl and ethyl, those are different. The identical groups are actually the 2 hydrogens. Those are the trans. So our hydrogens are the trans ones here. So if we're thinking about this double bond here, we're really talking about our hydrogens are the trans compounds. But what if we have different groups attached to the carbon? If we have different groups, we really can't use the cis-trans nomenclature. Instead, we're going to have to come up with something different. So let's say doing black. So if we had these 2 compounds, how would you be able to distinguish cis and trans? Do you have any of the same groups on each side? We don't, right? So how would we be able to decide between cis and trans and be able to identify these as 2 different compounds? For that, we use our EZ notation. And your next question is, what is the E and Z notation? That's used to assign stereoisomers. So when we do that, we come up with priority groups and prioritize the groups that are attached to the carbon-carbon double bond. And so we use the same rules that we did for stereochemistry to come up with R and S. We use those exact same rules to come up with the priority. So remember, first priority is based on atomic number. Then you try to pick which substituent has the larger group, the higher atomic number. If you have to go to the next carbon, then you go to the next carbon. So we follow the exact same rules we did for R and S for this case. Once we've decided which one has a higher priority over the other, then if the two groups are on the same side, we assign it a Z designation. And Z comes from the German word for zusammen, which means together. If they're on opposite sides, we assign the designation E for antigen, which means opposite. So if we look at those two groups again, here I have a fluorine versus a carbon. Since fluorine's heavier than carbon, it gets the higher priority. Same thing on the other side. Nitrogen has a higher atomic number than hydrogen, so it gets the higher priority. Then if we look at our second one, I have fluorine versus nitrogen, or fluorine here and carbon. So again, high, low. Now, since I switched the nitrogen and the hydrogen, hydrogen's a lower priority than nitrogen. So you can see the two high priorities are opposite on the E conformation, and the two high priorities are on the same side on the Z conformation. So this way we can start using E and Z instead of cis and trans when we talk about our double bonds. So this way you can start using E and Z notation when we discuss stereochemistry around our double bonds. So let's try and practice figuring out this E and Z conformation. So let's say we have let's say we have our two different compounds here, and you want to assign E and Z. Try and figure out which ones are E and Z, and then see if you get it right. Pause the video, try and figure out which ones are E and Z, pause the video, and then see if you get the right answer. So if we look at compound 1 and compound 2. For compound 1, here I have a CH2 and a CH3. This carbon is attached to 2 hydrogens and a carbon. This one is attached to 3 hydrogens. So we get a high priority and a low. Now we have a chlorine versus a CH2OH. Chlorine, heavier. So we get a high priority and a low. This means we have a Z conformation because our two high priorities are on the same side. Now, if we look at number 2, here I have a hydrogen versus the carbon. So high priority, low priority. Now we have a CH3 versus a CH2N. So again, high priority, low priority. This one happens to be Z as well. So you can see we're using the exact same rules that we used for the stereochemistry of R and S to come up with E and Z. And then once you come up with the E and Z, you would include that in the name of your compound. And then you also include the number to give the location of that double bond stereochemistry. So one last topic we want to discuss is alkene stability. Alkene stability becomes an important factor when we're looking at how the alkenes react and how likely they are to form a product. So if we look at these different substitute alkenes, I have a monosubstituted, di, tri, and tetra. So that means on the monosubstituted, there's one substituent and 3 hydrogens. On the disubstituted, there's 2 hydrogens and 2 substituents. Trisubstituted, just 1 hydrogen and 3 substituents. Tetrasubstituted, no hydrogens and 4 substituents. You can see we're having increasing stability with the more substituents we add to the double bond. And the reason for the increasing stability with the more substitution we get has 2 factors. One of them is an overlap of the electron orbitals from the substituent to the double bond. So having this stabilizing interaction between the substituent and double bond is also called hyperconjugation. Second one is the fact we're overlapping an sp2 and an sp3. That creates a slightly tighter bond and a slightly stronger bond because we're using an sp2 carbon. Another factor of alkene stability has to do with cis versus trans. Cis alkenes are always going to be less stable than trans alkenes if they contain the same substituent. And so our less stable isomer is higher in energy and therefore it gives off more heat. So if we have our cis versus trans and we draw an energy diagram, cis would actually sit at a higher energy level versus the trans. And it would have a higher energy of activation versus a trans. This alkene stability will come into play when we start learning about reactions that involve alkenes, and you have to predict the product. And so if you had to predict a product between a monosubstitute alkene or a disubstituted, the disubstitute would be more stable, so it'd probably be the major product. And so it's important to think about alkene stability during the course of a reaction and during the course of a mechanism. And so now you should know a little bit about alkenes and how to name them and designate them E and Z and stability.